8051 Output Interfacing Part 1. This is the pin configuration of the 8051. This is port 1. There are 8 I/O pins. They are named P10, P11, all the way to P17. This is port 0. There are also 8 I/O pins. This is port 2. This is port 3. Fall registers in the special function registers are mapped to the fall I/O pins. This is register P0, and it is related to port 0. This is register port 1. Port 2. Port tree. This diagram shows the memory map of the port registers. 80 is the bit address of the bit P0.0. All these represent the bit addresses. 90 is the bit address of the bit P1.0. 91 is the bit address of bit P1.1. 92 is the bit address of bit 1.2. Assuming this is the bit data in port register 1. This bit will appear at port 1.0. This bit will appear at port 1.1. These are the signals that appear at port 1. The set bit instruction, set a bit to 1. Set bit P0.0. Set this I/O pin to 1. Set bit P0.6. Set the I/O pin P0.6 to 1. The clear instruction, clear the I/O pin to 0. Clear P0.0. Clear this pin to 0. Clear P0.6. Clear I/O pin P0.6 to 0. The move instruction can change the data of the entire port. Example: move immediate 71 hex to port 0. This is the binary value of 71 hex. This signal 1 will goes to port 0.0. This signal 0 will goes to port 0.1. This signal 0 will goes to port 0.2. This signal to port 0.3, and so on. The immediate data 71 hex is moved to port 0. Connecting a output device such as a LED to the I/O pin. The LED is turned on because it is in forward bias. Change this signal to 1 to make the LED in neutral bias. The LED is not biased now, and the light turns off. The LED can be controlled by the logic at the I/O. The logic at the I/O can be controlled using the set bit and clear instructions. What do these codes do? This instruction: turn off the LED. This instruction: turn on the LED. The program jumps to label ham. The cycle repeats. The program runs in a loop forever. The LED blinks as fast as the instructions are executed. How do we slow down the blinking? Insert delays. When the L-call delay is executed, the program jumps to the delay subroutine. Time is spent in the delay subroutine. Blinking slows down. A buffer, such as the inverting buffer ULN2803, may be used to connect an output device to the I/O pin. Using a buffer allows a higher current to flow through the LED. The signal at the LED is inverted by the buffer. For example, if the signal is 0 at the I/O pin, it will become 1 when it reaches the LED. A logic 1 at the I/O pin will turn on the LED. A logic 0 at the I/O pin will turn off the LED. How do you expect the circuit shown to respond to the given program? Let's keep track of the contents in the accumulator and the port register in both hex and binary. Assume that the initial contents to be 0, therefore, all LEDs are not lighted. Accumulator becomes 1 on executing the first instruction. The second instruction copied the content in the accumulator to port 1. The rightmost LED is turned on. Trace the signal to make sure you know why this LED is turned on. The program delays for a while, and the LED remains on. The rotate left instruction shifts all the bit in the accumulator left by 1 position. The content in the accumulator is now 0 to hex. The program jumps to M1. The accumulator is copied to port 0 register. Again, the second LED is now turned on. The program continues to run, and the bits are shifted again. Content in accumulator becomes 0 for hex. The program loops again. Port 0 register is updated. Again, the next LED turns on. The bits continue to shift left with the RLA instruction. The accumulator becomes 08 hex. The program loops back again. Accumulator is copied to the port 0 register. Again, the next LED turns on. The bits continues to shift. The content in the accumulator changes. The program loops again. Port 0 register content is changed again. The next LED turns on. Another shift. Accumulator content changes again. Loops again. Port 0 register changes content again. Shift again. Accumulator changes again. Loop. Port 0 register changes. Shift. Accumulator changes. Loop. Port 0 register changes. The bit 1 is shifted to the LSB position. The accumulator becomes 01 hex again. Another loop back. The lighted LED goes back to position 1 again. This is how the program would run. How do you expect the circuit shown to respond to the given program? Let's keep track of the content in the accumulator register R7 and the port register P0 in both hex and binary values. The first instruction causes the accumulator to become 01. R7 is initialized to 08. Content in the accumulator is copied to port 0 register, and the data are reflected at the I/O. One LED turns on. The delay routine call slows down the program. Bit in the accumulator are shifted left one position, and the content in the accumulator becomes 02. R7 is decremented by 1. If it is not equal to 0, the program jumps to M2. R7 becomes 07, and the program jumps to M2. The move accumulator to port 0 causes the content in port 0 register to change. The LED is affected by the change. The rotate left accumulator instruction causes the beat in the accumulator to shift left again. R7 decrement from 7 to 6, and the program jumps back to M2. Port 0 is updated, and the signal at the I/O change. Beat in the accumulator is shifted again. Accumulator becomes 08. R7 decrement from 6 to 5, and then jump to M2. Port 0 register is updated, and the I/O signal changes. Beat in the accumulator are shifted again. R7 decrement from 5 to 4, and then jump to M2. Port 0 register is updated, and the I/O signal changes. Beats in the accumulator are shifted again. Accumulator becomes 20. R7 decrement from 4 to 3, and then jump to M2. Port 0 register is updated, and the I/O signal changes. Beat in the accumulator are shifted again. R7 decrement from 3 to 2, and then jump to M2. Port 0 register is updated again, and the I/O signal changes. Beat in the accumulator are shifted again. R7 decrement from 2 to 1, and then jump to M2. Port 0 register is updated, and the I/O signal changes. Take note that the LED has traveled from the rightmost end to the leftmost end. The 1 in the accumulator is shifted left all the way back to the LSB position. Another decrement of R7 results in R7 to become 0. This instruction does not jump back to M2, but continues forward. Accumulator is initialized to 80. R7 is initialized to 08 to prepare for another loop of 8 times. Accumulator content is copied to the port 0 register. Beat in the accumulator are shifted right by 1 position. R7 is decremented from 8 to 7, and the program jumps 2 and 1. Content of the accumulator is copied to the port 0 register. Signal at the I/O are updated. The status of the LED changed. Beat in accumulator are shifted right by 1 position. The accumulator becomes 20. R7 is decremented from 7 to 6, and the program jumps 2 and 1. Content of accumulator is copied to the port 0 register. Signals at the I/O are updated. The status of the LED changed. Beat in the accumulator are shifted right by 1 position again. R7 is decremented from 6 to 5, and the program jumps 2 and 1. Content of accumulator is copied to the port 0 register. Signal at the I/O changed. The status of the LED changed. beat in the accumulator are shifted right by 1 position. R7 is decrement from 5 to 4, and the program jumps 2 and 1. The cycle repeats until R7 becomes 0. Another decrement of R7 results in R7 to become 0. This instruction does not jump back 2 and 1, but continues forward. The short jump M1 instruction causes the program to jump to M1. The program cycle starts all over again. The LED runs forward and then backward. The cycle repeats forever. How do you modify the previous program for the LED to run in the manners shown? Let's take a look at the code. To light up the third LED at the start, immediate 4 should be moved to the accumulator. There are 4 positions of the LED to be lighted. Therefore, the loop should run 4 times. R7 should be initialized to 4. On the reverse run, the LED starts from the 6th LED. Therefore, 80 hacks should be changed to 20 hacks. Similarly, the LED reverses 4 positions. R7 should be initialized to 4. The changes are highlighted in red.